All right, let's have a look at another kind of annuity now. These are called deferred annuities. Now, deferred annuities are annuities where payments start at a later date. We've already done a lot of annuities on timelines at various points, so these may seem a little bit familiar, but this particular version happens often enough that we give it its own name. So basically with a deferred annuity, we put some money in at an earlier point in time, maybe when a child is born or something like that, and the money stays in the account and earns interest for some number of periods, maybe until college age, and then the annuity payments start to come out. So what's happened is that original amount has had a chance to grow much bigger, or in other words, the parents in this case could put a little bit less in than they would have otherwise because they've got time on their side. So that's the idea behind a deferred annuity. They're really just ordinary annuities where the first payment is deferred or delayed for a certain number of periods. If we look at a timeline, on the timeline we have our annuity over on the right-hand side, and let's just treat that like an ordinary annuity. We could do it as an annuity due, I suppose, but then we'd have to adjust our period of delay by 1. So let's treat it like an ordinary annuity, have end payments. And then we've got this delay period or period of deferral from when the money is originally put in down at the 0 point up until when the payments start. The formula for a deferred annuity looks like this. It's always present value, by the way, that we're dealing with. We're always interested in putting the money in early and letting it earn interest. So we're going to put in our annuity enough money for all of those payments. Well, here's the payments, and here's the period of time that we're waiting. I've used the little letter D in the formula to represent the period of deferment or the time we're waiting. It's also given in periods. You could be thinking, why didn't we use N then? Well, we've already got an N on the go in our equation, and so we don't want to mix the two up. So we use little d instead. So that's not too bad of a transformation. Let's see if we can have a look at how a few of these work. All right, let's have a look at an example here. We have a couple wanting to set up a college fund for their granddaughter. They want her to be able to take out $3,000 every quarter while she's in college. Her first withdrawal is going to be in 5.5 years, and the fund can earn 7.2%. How much should they put aside today to make it all work? I'm going to draw a little timeline here. On my timeline, I'm going to put in 5.5 years. That means the next payment would be 5.75 years onwards until we get to the end. So there's a payment of 3,000, another payment of 3,000, all the way out to the end. We said quarterly for 3 years, so N would be 12, wouldn't it? There'd be 12 payments there. Let's just think for a minute though, where does the term of the annuity go? Does it go from here to there? That doesn't look quite right, does it? Because if we remember how annuities work, ordinary annuities, the payment is at the end of each period, isn't it? So we have to make sure that when we draw the term, we actually take it right out to the beginning of where the first payment period starts. It's periods we're looking at, not payments, remember. Periods are what count. So first period is there. That's at 5.25 years. That's really crucial because if we don't do that right, then little d is going to be incorrect. So d in this case then will be 5.25 years times 4 times per year. That's 21 periods. They gave us a rate as well. J4 is equal to 7.2%. I is equal to 0.018. So if we can work out the present value now for this deferred annuity, and that's going to be the amount back at the 0 point. That's $3,000 payments, and we want to discount 12 of them. So that's just the same old formula we've been using for a long time now. And then I'm going to bring that money back to the 0 point. That's what the deferral does. If we plug all that in there correctly, we get the final answer of $22,083.19. So what we're saying is if they put $22,000 roughly in the bank today, it'll earn interest and become large enough that in 5.5 years she can take out her first end of quarter withdrawal, and she can continue to do that for 3 years. That's a deferred annuity. Now, there's a couple things to think about here. Why did I use 5.25 when I worked out D and not 5.5? Well, remember, 5.5 is where the first payment is. 5.25 is where the ordinary annuity began. It's kind of like on our original timelines. Remember, we had 0, 1, 2, 3, etc. On the timeline, we defined the term as starting at 0, didn't we? Even though the first payment was at 1, the term actually started at 0 because that payment covered us all the way off for that whole first period. Always, always, always remember, with annuities, it's periods that count more than payments. The payment can happen at either the beginning or the end, but it's the periods that count when we're counting things. All right. Let's have a look at another example now. Mrs. Savard purchased a deferred annuity for $10,971. It's going to provide 16 quarterly payments of $1,000. Money can earn 6%. If the first payment is going to be received on October 1st, 2015, when did she buy it? So I've done a couple things here. First off, I've thrown in some real dates so we can work on those. But I've also flipped it around. We're really trying to solve for D in this case, aren't we? So let's see if we can get the logic right on this one. Here's a timeline. We want to find the date that she bought this whole annuity. The first payment comes out on October 1st, 2015. And they're quarterly as well. So there'll be another payment coming along 3 months later. Let's see, November, December, January 1st would be the next payment, wouldn't it? And I'll just go ... to show that there's more coming. In fact, she wants 16 quarterly payments or 4 years worth. Now, just like we talked about a few minutes ago, if the first payment is October 1st, that must have been the end of the quarter that started on July the 1st. So I'm going to go and put that on the timeline as well. So when I'm drawing my term, with my 16 payments on there, the term begins on July the 1st. Again, that's going to be really important if I'm going to solve for little d correctly and get the right date. Now, we could actually label the end of the timeline. It's not important for the question, but now that we have the beginning date of July 1st, 2015, we know we're going to go all the way out to July 1st, 2019. Right, it's going to take us out to the very end. Let's not worry about that too much. First step, I'm going to find the present value of the annuity that we've got on the timeline. So step 1, the present value of that annuity is $1,000 payments. Let's bring those back. Oops, I need a little rate, don't I? I was equal to 0.015. It was 6 over 4. So 1.015. There's 16 payments. 0.015. That gives me a value of $14,131.26. That's how much the annuity is worth on that date. Mrs. Savard, though, only put in $10,971. So we now have to, for step 2, find how long it will take for $10,971 to grow to become $14,000. What's little d? You could draw the arrow either way. I just want to say there's a time frame in there that I'm trying to find. Now, let's write that as a question. How long will it take for 10,971 to become 14,131.26? If you think back for a few chapters now, back to when we're just doing pure compound interest, we had a formula for finding how long when we just had two single amounts of money, a future value and a present value, and that's really what we've got here. The present value is 10,971. It has to grow by July 1st to be 14,131. Then it'll fund the annuity. So let's go ahead and use that old formula we had from a few chapters ago and put that in there. Future value over present value divided by the log of 1 plus I. Pop that in there and come up with 17.00. And always when we solve for n, or in this case, little d, isn't it? That's really what we're trying to solve for. We're using the old n formula, but it's actually d. We end up with 17, and it's in quarters, isn't it? Because that's what the rate was. 17 quarters is also 4¼ years. Either way we can look at it, doesn't matter too much. What's important now is I have to start at my July 1st, 2015 and work backwards 4¼ years to get to my unknown date. Well, we can do that. Let's see, 4 years away would be July 1st, 2011. Another ½ year is 3 months, so that's June, May, April. And so that gives me April 1st, 2011. That must be when she put the money in the bank. Now, you could try it if you like and work it in reverse. Put 10,971 in as PV. Add interest to it for 17 quarters. You should end up with 14,131. Put that in as your present value. 1,000 for your payment, 0 for your future value, and then and your interest rate, and then calculate n, and sure enough, you'll get 16 payments out. So that's kind of doing it in reverse, solving for D. Let's go ahead now and give you a chance to try one out. See how you do. Let's say that I'd like to retire in 10 years, and I think that I'll need 50,000 at the end of each year while I'm retired, and that I'll be retired for 30 years. To fund that retirement, I'm going to invest a lump sum today, which will earn interest until retirement, and then fund the withdrawals. So I'm going to put a lump sum in now, but it's going to grow, isn't it, to become a little bigger. And then it's going to fund my withdrawals. How much should that lump sum be? And let's use a rate of 6% annually. Everything's in years. Like we've done before, I think the best way for you to deal with this is to press pause here and try it out. And when you're ready, press play again and come on back and see if what you came up with matches what I've done. All right, welcome back. How'd you make out with this one? Let's have a look. Here we are now. I'm going to retire in 10 years, aren't I? And then I'm going to start taking out withdrawals that are going to last for 30 more years after that. Even though I retire in 10 years, my first withdrawal comes out at year 11 because it's the end of that year, isn't it? I said they were year-end withdrawals. And they're going to carry on for 30 years. So here's my annuity right there. N is equal to 30. What's little d in this case? Well, little d here is simply just 10 because they've already, in this question, given you sort of the reference points. The question could have said, oh, the first withdrawal will be at year 11. You would have subtracted 1 to get 10. This time we worded it to give you the 10, but then said that the withdrawals are year-end withdrawals after that. So that's our little d up to that point. So our question is, how much should we put aside down here as our lump sum to make it all work? Well, let's go ahead and put in our withdrawals of 50,000. And we're going to bring that back at 1.06 for 30 years. I didn't write the 0.06 up there, so I better do that. And then we're going to take whatever that amount is and represent it in today's dollars, bring it back a little further to today, just like that. If I go ahead, enter all those numbers in correctly, well, let's do it 2 stages here maybe. How's that? I'm going to first put how much I'm going to need on the day I retire, 688,241.56. And then I'm going to bring it back. So I'm doing it in 2 steps, just in case you did as well. If we put that all together now, find that I could put in $384,310.49 today. And that would be enough. That would grow to turn into $688,000 on the day that I retired, which would then be enough to fund those withdrawals of $50,000 a year for the next 30 years. That's a good deal, isn't it? Now, could we have a deferred annuity due? And we could. In this case, we're going to define the annuity as an annuity due. And that means the deferment period is really up to where the first payment is. So it didn't end here. It ended up here, one more. That's kind of the other way of looking at it. What if I wanted to use my annuity due formula instead? What would the transformation be? Well, it's really the same thing if we think about it. Here we've got the formula for an annuity due all the way up to there. And then we have a little part here to bring it back. What happens in this case, though, is small d is actually 1 bigger than it was when we were doing them as ordinary annuities, because we're going all the way up to the first payment. So if I've got 1 plus I here, and then 1 plus I to the negative d, and d is a little bigger, that's going to kind of wipe each other out, and we'll be back essentially to what we had before. Let's have a look. Let's say I want to retire in 10 years, and I project I'll need $50,000 at the beginning of each year in my retirement, which I expect to last for 30 years. I'm going to deposit some money today, and I can earn 6%. So exactly the same question, except this time I want the money a little bit earlier. I want it to come out at the beginning of each year. If you like, press pause now. Give this a quick try. And when you're ready, press play again, and I'm just going to carry on. So in this case, my first withdrawal does happen at 10 years. A little bit different wording on the question, didn't we? And I'm going to take out a bunch of them all the way up to when I get to the 40-year mark. But remember, that last withdrawal at year 39 would actually cover me off going forward because it's an annuity due. Well, in this case, there's my annuity due. N is equal to 30. I is 0.06. And then we're going to take whatever we get there as the present value for the annuity and bring it back to get a present value overall. $50,000 a year brought back for 30 years times 1 plus I. That's the annuity due part, isn't it? And then from there, I'm going to bring all of that back 10 more years. If we work all of this out, I get a slightly bigger number, 407,369.12. So compared to the one we just did a few minutes ago, we're going to need just a little bit more money in there to make it work out, because I want to have those withdrawals at the beginning of each period. So I'm going to have to put in about an extra $23,000 to make it all work. Let's just think for a quick minute here. The question's done. We're good. But could I have handled this with the formula I used a few minutes ago, just the one for ordinary annuities? And I could have. Let's do that on the bottom. I would have said, okay, that would kind of look like this, wouldn't it? I would go from 9 to 39. N would equal 30. And then D would only be 10, or 9, not 10. Right? Remember we had D was equal to 10 up top before. Now it's only 9 because we're going back from 9 back to 0. So over here, I would have had 50,000 times 1 minus 1.06 to the negative 30 over 0.06 times 1.06 to the negative 9. That equals exactly the same thing. So what's going on there? Well, it doesn't really matter which tool I use as long as I get my frame of reference correct. If I want to treat it like an annuity due, the deferral goes up to the first payment because that's where the term begins. If I want to treat it like an ordinary annuity, the deferral goes up to the beginning of the term, which is actually one period before the first payment. Can you see that 1.06 to the power of 1 times 1.06 to the negative 10 combined become 1.06 to the power of negative 9? We know when exponents are like that, we can combine them, can't we? So it really does work out, and it makes sense. So you can use either tool. If you're looking at annuities, you have to think, well, where's the first payment? Conceptually, where do they want me to look at the beginning of the term? Is there an easier point or an obvious one based on the wording? And then pick to do it as an ordinary deferral or as an annuity due deferred. Either way, though, as long as you've got your frame of reference correct and you've adjusted D appropriately, you should come back to the same answer. There's lots of these to practice in the book. Work your way through them, and when you're ready, we'll move on to a final type of annuity in this chapter, and that's called perpetuities.